So we'll try to understand where or how this fits into the process of guidance through this talk. So here's a brief outline of how the talk will go. We'll start with an introduction, a very general introduction of guidance in general, and then we'll narrow down into the specific problem that we'll be handling in this work. And then we'll talk about the more theoretical aspects of how we are trying to address the problem. And I'll try to show some hardware implementation videos just to, they are always more interesting than the theoretical things. And finally, we'll conclude the talk. So let's get started. Okay, so some introduction and motivation towards what we will be talking about on this talk. So let's talk about something which is called wheeled mobile robotics. Now, what exactly is wheeled mobile robotics? So, as the name suggests, it's dealing with mobile robots which are wheeled, as simple as the name suggests. So, where are they used? Where are wheel mobile robots used? Where is wheel mobile robotics applicable? So it is used in several real world systems. For example, let's say an agricultural robot. Nowadays, if you go to countries like Germany, people are already using, so Germany is an example. There are several other countries which are doing it. So you can find robots working autonomously in agricultural fields. And several rovers for planetary explorations have wheels in them, and the theory of wheel mobile robotics can actually be applicable for them as well. Also, another thing is people are also using these robots for applications like surveillance as well. So, and these are just a few of the applications. So, even general day-to-day transportation that we use, cars, buses, trucks, all of these things fall into the broad uh, umbrella of wheeled mobile robotics. So, now, uh, let's see. So, wheel mobile robots, the study is interesting because, first of all, such robotics is actually applicable to real world vehicles. And whatever we work with them, we can actually implement it in hardware or in a real world system. As I mentioned, some examples would be systems like cars, even a bicycle, underwater vehicles like submarines, aerial vehicle like fixed-wing aircrafts, so on and so forth. So what are the challenges that comes into picture when we deal with wheeled mobile robots? Now, wheeled mobile robots generally come with something which is called non-holonomic constraints. So we'll not go into the details of that, but just to let you know that these models actually uh, make it difficult for us to handle the nonlinear or the robot that we are working with. And such robots generally have nonlinear models, which in general also makes working with them more challenging compared to a linear model. Now, the specific wheeled mobile robot model that we'll be working on is a unicycle. Now, what is a unicycle? So, as the name suggests, a unicycle consists of one wheel. Now, it has something which is, we call it 2 degrees of freedom. So, let's understand it. What is a unicycle and why does it have 2 degrees of freedom? So, now a unicycle is actually a single wheel. And if you imagine, now the directions in which a wheel can go is either forward or backward, or it can turn left and right. For example, if you're riding a bicycle, you know that if you turn the handle, the wheel would actually go left or right. And depending on how fast you're pedaling, the wheel can, like, that will determine whether you're going forward or backward and how fast you're going. So basically, in general, a unicycle system, a single wheel system, only has 2 degrees of freedom through which we can access or control it. One is the forward speed or backward speed. Let's call it the linear speed, which can be forward or backward, and the turning rate, which is either left or right angular rotation. So these are the only 2 degrees of freedom through which we can control a unicycle. Okay, so what is the reason behind choosing a unicycle model? Why are exactly we working with this system? So that is a very important question, and let's try to understand that. Now, a unicycle is a point mass system, which is a very simplistic model. We assume that it is a point mass model, like it's a single wheel system. Not only that, we also assume in most of the guidance applications that it is a point mass system. So why does the study of a point mass system is why is it even relevant, given that wheel mobile robots are such complex systems like a Mars rover or an agricultural robot or a truck or a car? These are very big systems. So why are we working at all with a point mass system? Now the answer to that question is that even today, like generally, there are several aspects in a guidance process. Now, the first process, let's say we are talking about designing the trajectory of a vehicle or designing the path of a vehicle. Now, howsoever complicated the system is, be it a missile, even a fixed wing aircraft or a submarine, all of the systems which can be modeled as a unicycle. So basically, a unicycle, although the name sounds like it's a wheeled, it can only be applicable to systems which have wheels. But actually, a unicycle is a very broad framework. It can be applicable to any object which can go forward or backward or and turn left and right. Anything which can do these two things can actually be modeled as a unicycle. So even an aircraft which is moving in the air can actually turn left or right or go forward, or like it has a linear motion. So that also falls into the broad category of a unicycle system, or its simplistic model can be related to a unicycle. The same goes for a submarine, the same goes for a missile, and cars, and several more vehicles. So first of all, unicycles are extremely relevant to several real-world systems. The second thing is every trajectory planning operation in a guidance process actually deals with designing a trajectory for a point mass system. So how do we apply it to a complex real-world system? What we do is we take this point mass model. For example, let's talk about a car. Now, as I said, a unicycle can go forward, backward, or turn left and right. So what would be the difference between, like motion-wise, what would be the difference between a car and a unicycle? Now, the difference is that a car, along with, just the heading rate, there are two things. There's a steering rate and there's a turning rate of the wheels. So that is the difference between a car and a unicycle. So if you see, there's no direct correlation, like it's not a very linear model how much you're turning the steering. If you've ever tried driving a car, like the amount by which you turn the steering wheel is not exactly the same amount by which the wheels rotate. So that is why what we do is when we want to go from a unicycle to a car, we need to add another term to the model, which is a steering rate, the rate at which the steering wheel is turning. So what I'm trying to explain here is by simply adding one more term to the unicycle model, we could actually arrive at a kinematic model of, let's say, a very simple car. Now, if we want to apply it to even more complex systems, what do? We just add more and more complexities to it gradually. So that is why whatever model we work or whatever trajectory we plan with a unicycle can just be, we can make slight changes to the model and actually apply it to several complex systems, which can be very gigantic systems like missiles or aircrafts and things like that. So this is why the study of unicycle is extremely relevant, and even today, even in industries and academia alike, most of the works that we see actually deal with unicycle systems, with point mass unicycle model. And another thing is what we mostly work with. So there are two different kinds of models. One is a kinematic model and the other is a dynamic model. A dynamic model has all kinds of forces and torques, all the physics getting into it. And so a model that we get, a dynamic model, generally consists of these terms as well. However, when we go to a kinematic model is generally a motion model where we do not actually care about what kind of force is actually making it turn. But what we rather care about is how much it has turned. So it is only a motion model which will tell you on some plane, or maybe in 3D or whatever plane that we are working with, or whatever domain we are working with, what would be the motion of the system? What kind of model would describe only the motion of the model? And such models are known as kinematic models. So in motion planning algorithms or in guidance applications, what we generally work with are kinematic models of systems. Okay. So basically, this is a general idea of why a unicycle why a study of a unicycle is extremely relevant even today for industry and academia alike. Okay, so now let us look at some things that one can do with a unicycle. Or is there any broad category or something into which we can divide the tasks that a unicycle can do? So, speaking from an uh, and perhaps an academic perspective, maybe. So, generally, the motion tasks that a unicycle can do can be broadly divided into two categories. The first one is a regulation problem. The second one is generation of desired trajectories. So we'll discuss these 2 points one by one. So let's first talk about a regulation problem. Now, what is a regulation problem? So it's called regulation to a point. So what happens in these problems is that we have two categories again. The first one is point stabilization. The second is posture stabilization. Now, what are the differences between these two things? So let's understand it. Now, in a point stabilization problem, let's imagine a car. Now, it would mean that you are sitting at some point A and you want to reach some point B. So, in a point stabilization problem, you only care about designing a path so that you will start from point A and you'll reach point B. Now, what is posture stabilization? Now, in posture stabilization, we actually say that now again you have a point A and you have a point B. Now, when you reach point B, you should also reach there with a specific heading angle. Now, where is this applicable? So, imagine a car parking problem. If we want a car to park itself autonomously, now, let's say in a parking slot, a car cannot, go there arbitrarily. It has to get in there with a specified heading angle. So this is the difference between a point stabilization and posture stabilization problem. The heading angle comes into picture in the latter. And in layman terms, it's known as the car parking problem, the posture stabilization problem. Now, other than regulation problems, motion tasks related to a unicycle can also be used to generate any kind of desired trajectories. What are the examples? Now, people use it for trajectory tracking, path following, and even, to generate several perhaps interesting looking paths. So, which some of them are shown here. Now, in the diagram C, we actually see some very interesting paths, and all of these paths actually generated by a unicycle. And the second figure here shows a path following problem where one can see that, let's say, our reference trajectory is shown in dots, and the actual trajectory of the unicycle is actually shown as a solid line. So we see that through this figure, in a path following problem, we are required to track or trace the path, the desired path, which is given to the system. Now, in general, so these are, let's say, these are the motion tasks that we do. So fair enough. So is it always sufficient to only look at the task at hand, or in general, are there any other constraints that one has to deal with in guidance applications? Well, the answer to that is yes, there are several other constraints other than the task in hand, which one has to take into account. Now, what are they? The first category, let's say we call it vehicle-specific constraints. Now, what are vehicle-specific constraints? As the name suggests, these are constraints or limitations pertaining to the vehicle itself or the agent itself that we have. Now, some examples of that would be, let's say, input saturation or sensing capabilities of the system, or even the vehicle dynamics itself. Now, of course, there could be constraints related to the environment as well. Now, and what would they be? Let's say presence of obstacles. Now, this is something which we encounter very, very commonly in real world systems. And other thing is a shape of the environment could also be an issue, like in case it's not very smooth or something, one has to take that also into account. So in general, in a typical guidance problem, what one has to do is to, uh, imagine the task at hand and also take into account, other than the task, the vehicle specific constraints, environment specific constraints, and if there are any other constraints. Okay, so now coming to the problem statement that we are looking at in this work. So we talked about the motion tasks that a vehicle can do, and we talked about some constraints that can, perhaps affect the paths that the vehicle can take. So in this work, what we are trying to do here is we are trying to study a general framework where we say that we imagine a constrained scenario where a unicycle system is actually constrained only like constrained in terms of its sensing capabilities. So it can sense very little information. Now, our objective was to actually study. Our objective was actually to study what kind of trajectories can be generated using this unicycle system. And then we eventually go on to show that the trajectories that we get using this constraint framework can actually be applied to solve several problems like boundary surveillance. It can be used to solve even a point stabilization problem. So just to walk you through what we are going to see in this talk, we will look at a constraint scenario. We will try to find out what are all the feasible trajectories that this unicycle system can take, and eventually we'll see what kind of applications we can solve using the trajectories that we get. Okay, so these are the underlying constraints and objectives in this work. We assume that we have access to only limited information, and we also incorporate, in fact, actuator saturation constraints into our framework. And assuming these two things, we try to analyze all the feasible trajectories that one can get using a unicycle system. And then we show that the trajectories that we get can actually have certain applications in several systems, like let's say oil spill monitoring, landmine detection, and so on. Okay, now specifying things a bit more. So what is this limited information that we are talking about? So the limited information that we are talking about is a distance information or range information with respect to some other target point or some other point. So we generally call it the target point with respect to which we are always calculating the distance. As I mentioned, the autonomous agent that we are working with has unicycle kinematics, and our objective is to study its feasible trajectories in this constrained framework, and with a hope to, or with applications in mind, we actually show that we can control a lot of the aspects of these trajectories. We provide some techniques to do that. And then we show the applications or the specific applications. So here are some examples of the trajectories that can be generated. So the first one can be used to, broadly speaking, can also be used to satisfy or solve or address, let's say, coverage kind of applications, which would be landmine detection or oil spill monitoring. The second curve shown in the figure can actually be used to solve problems like surveillance, where what the agent would do is it will keep monitoring continuously the region in that area, the region shown here. And the last figure, actually, this is a very neat figure, but the last work actually pertains to solving a boundary surveillance problem where we can, in fact, generate the guidance commands so that the unicycle can actually continuously monitor any arbitrary boundary, irrespective, like boundary of any arbitrary shape. So this is the just an example of how these different trajectories that we generate can be used to address real-world applications. Okay, so here is a mathematical framework of what we are going to do. So let's talk about the most important things that we need to deal with. So one can only focus on this figure. So let us say the agent that we have, we denote it as A, and we have a target point, let's say, which is just some stationary point. Now, when we say it is a constrained information framework, we say that the agent can actually measure only the distance information pertaining to this specific point, which is the point of interest. So this can be any building of interest or any beacon or anything like that. Okay, now coming to the agent A. Now, as we mentioned before, the agent can move forward or backward. Let's say it has a forward speed given by V as shown in the figure. Now there's only our objective is to, let's say we are trying to solve a surveillance problem. We are trying to, which is called repeated boundary coverage or repeated surveillance. In a repeated surveillance problem, perhaps if you have a building of interest, then the objective there is to periodically keep making rounds around the building. So now in order to address that problem, the vehicle also has to know, like also has to keep looking at perhaps the target while doing so. So what angle or what parameter actually defines where you're looking? So that is the angle phi. So that means there are two parameters of interest here. The first one is the distance between the agent and the target. And the second one is nothing but how far away you're looking from the target. So which is just given by this angle phi. Now throughout our analysis, we'll only use these two terms, which is r and phi. R is the distance, phi is the angle by which you're looking away from the target. So that means if phi were 0, you'd be looking directly at the target. That's it. Okay, so now this is the kinematic model of the unicycle system. So as I mentioned before, we can control it using two terms. One is the forward speed and the other is the turning rate. Now the forward speed is controlled by the term V, which is given here. And the angular speed, in fact, can be controlled by the term U, as given here. Now in our work, we assume that the forward speed V is actually constant. Now, why have we done that? How does it help us? So generally speaking, the motivation behind this was that like implementing also the idea here was to improve upon the hardware implementability of the work. That's why we assumed a constant speed model, which would be easier to implement compared to a varying speed model. Okay, so now what we do, so we have these three terms, which is x, y, alpha, pertaining to the position and the heading angle, let's say. So we do a coordinate transformation, we convert everything into a polar coordinate frame, and we actually do some substitution, and we see that the entire model of the unicycle can actually be written in terms of these two variables that we talked about, which is r and phi. And we showed these two terms here, as given here. Now, if you look closely at this differential equation, you'll see that the only variables here are r and phi. V is a constant and u is the input that we will choose. Now, so just to remind you, we have assumed here that it is it's a constrained information framework. So we assume that, let's say the sensors that we have can only give us one information, which is the distance with respect to the target point. Let's say we cannot do, somehow we are not able to measure any other things. So what would we do? How would we do it? And in this case, what would the input actually look like? Let's see. So this is where the generalized control scheme comes in. Now, our interest here was to analyze uh, all kinds of possible trajectories when the range information is given. How would we do it? The only possible way to do it was we assume that let the input be any arbitrary function of the distance, which is like it could be any arbitrary function as long as it is continuous. This was the only assumption that we had, that if f only needs to be continuous. Now, what do we do? So we substitute this in the differential equation, which only consisted of the terms r and phi. And we do some more maybe rearrangement, and we solve the differential equation completely, and we arrive at a very neat looking expression, which is known as g of, which looks like this, g of r being equal to minus vr sine phi. Here we have assumed that our input u is f of r, okay, and so and we solve the differential equation, we make certain rearrangements, and we get our input or a final looking solution of the differential equation as this, g of r being equal to minus vr sine of phi. Okay, just to let you know that mathematically speaking, what g of r looks like is this. G of r is equal to some function f tilde r minus k. K is nothing but the constant of integration, and f tilde r is actually the antiderivative of the term r f of r. All right, so now finding this generating function actually solved a lot of problems for us. It allowed us to like find a unified solution where we could say that, where we could show that the trajectories that we get can actually be broadly categorized into only three types, which are shown here. The first one is some annular trajectory, the second one is a circle, and the third one is a spiral. So by using the properties of this generating function, we actually proved that only these three kinds of trajectories are important. And from this point onwards, we will not be using any other mathematical equation which we have talked about till now. We'll forget everything else. We'll just focus on this one expression, which is g of r equals minus vr sine of phi. Okay, so let us first talk a bit more about the generating function. Like, since we mentioned that we'll be using it, so let's talk a bit more about this generating function. Now, generating function in general, as I mentioned before, it is given as f tilde r minus k, where k is the constant of integration and depends on the initial conditions. And f tilde r depends on the input which is given to the system, f of r. So basically, whatever f of r we choose and the initial conditions we choose, that will actually define what a generating function would look like. Okay, now let's say we'll come to this plot now. So let's focus at this equation again, which is the solution of the differential equation. So we'll keep coming back to only this one equation, which is g of r equals minus v sine phi times r. So what does this actually mean? This means that first let's focus on the right hand side, minus v sine phi times r. So sine phi we know can vary between +1 and -1. So that would mean that the RHS here can vary between plus VR to minus VR. So let's first plot these lines. We have some plane here, some region here, and the argument is R here. So we have just plotted some straight lines where the maximum slope of the straight line is plus VR plus V, and the minimum slope is minus V. Okay. Now generating function. So again, if we focus at this, the generating function depends only on R. It is a function of R alone. Okay, so that's why it's written as g of r. So if you solve the differential equation and if you substitute the value of f tilde r, so you'll find that it cannot be a function of anything else. Now what we do, or what is the solution of the differential equation? Now the solution of the differential equation actually corresponds to the intersection point of the generating function g of r with the lines minus v sine phi times r, these straight lines. So let's look at this figure. Now let us look at the generating function shown in orange here. So now we see that the generating function intersects the region or intersects the line minus v of r at point A. So this means point A is in fact a solution. Now we see that it is also intersecting all of these lines up to the point when it reaches the straight line v of r. So beyond this point, there'll be no interaction. So that means every point in this region will actually be a solution. So because of this, we call this region in gray as the shade, as a feasible region. Okay, so feasible region is just nothing but the region between plus VR and minus VR, because only in this point can the RHS exist, and hence a solution is defined only in this shaded region, which is denoted by plus VR and minus V of R. Okay. All right. So, okay, so basically what we show here is that, so what kind of phi does every point correspond to? So of course, if the slope is minus V, then sine phi is equal to 1 and phi is equal to pi by 2. That means the lowest line here will correspond to phi equals pi by 2. And similarly, the highest line here will correspond to phi equals 3 pi by 2. All right, and we call this the feasible region. Okay, so now we'll not get into the details of all of these points here, but let's focus on some of the interesting things. Now we see, as I mentioned before, now this region, we just always call it the feasible region. Okay, now, and the intersection point of the generating function with the feasible region actually gives us the trajectory. Now, so let's look at the generating function in red. So now we know that the solution of the differential equation will only correspond to the region between points A to B. So this is when the solution is defined, okay? And if we look at the generating function blue, we see that solution will not be defined for this case. All right. So now the question is, so we mentioned that, let's say the solution is defined only when it is inside the feasible region. Let's look at the generating function in magenta here. So it will only be defined when the generating function is inside. So that means, let's say the region A to B, and the region, say it looks like C to infinity. Okay. Now, what do I mean when I say the solution is defined here? That means, let's draw the corresponding lines. So if this is the value of the generating function, so when the generating function is here, the corresponding R value is given by R of A. Similarly, the corresponding B value will be given by R of B. Now my solution of the differential equation, which is nothing but the feasible values of R. Remember that the differential equation that we solved consisted of terms R and phi. So what we are trying to find through this is what are all the feasible values of R. That means if you imagine the target sitting somewhere, so R is nothing but the distance from the target. So how far away from the target are you going, or how much close to the target can you get? Okay, so this is what R signifies. Now we see that a solution is defined only when my parameter R lies between RA to RB and RC to infinity. Now between RB to RC, there's no solution. Okay, so let's look at it. So since we call this a feasible region, now if the generating function, for example, in this case, there are actually multiple feasible regions. So feasible region is nothing other than the fact that the generating function is inside the shaded region. So we see that in this case, there are multiple feasible regions given by this, the union of RA to RB along with RC to infinity. All right. Now the question arises is that, let us say since we are dealing with a general f of r, now which could be any control input. So how do we know what kind of feasible regions we will get inside? How many kinds of intersections are possible? So we'll try to understand these things graphically. So let's look at the graph here. All right. So before we talk into how many kinds of subsets, okay, are possible in SK, or how many multiple of feasible regions are possible inside SKFF, let's define some more terminology which will just help us in speaking about these things in a more easy way. Okay, so let us consider this generating function in green. Now it enters the feasible region at point A. Now we call this point where the generating function enters the feasible region as an entry point. And the point where it exits the feasible region, we call it an exit point. And the point where it is tangent to either one of the plus VR or minus VR lines, we call it a tangential point. So we can also come up with mathematical expressions of what defines these points. But the idea is that one has to note here that in this particular figure, we see that the generating function enters through the shaded region by intersecting the line plus VFR. It even exits through plus VFR. However, it's not mandatory. Now, for example, I can also draw a generating function which enters here and exits somewhere here through minus VFR. Similarly, it can also, so there are several combinations which are possible. However, just for consistency, wherever it enters, we call that the entry point, and wherever it exits, we call that the exit point. And if at all it is tangent at any point, it's not mandatory. A generating function does not always need to be tangential to any of the plus VR or minus VR lines. However, if for some generating function there exists a point where it is tangent, then we call it a tangential point. All right. Now, this will enable us to talk about some more things. So coming back to the question of how many kinds of trajectories or how many kinds of feasible regions are actually possible in general for a given generating function. So just speaking solely graphically, like looking at the graph, one can conclude, let's say, that only 5 kinds of subsets are actually in fact possible. Like any kind of arbitrary generating function that we draw corresponding to any continuous input f of r. So one can imagine, in fact, any weird looking function f of r. Converting the problem to the generating function space, we see that only 5 kinds of regions are possible where, in fact, we'll have multiple feasible regions. So let's understand this through the graph. Now, we can have, what can the intersections look like with respect to the generating function? So again, let's look at the generating function here, given in green. Now we see here that first kind of intersection corresponds to the generating function actually entering and exiting the feasible region. So this is one kind of a subset or one kind of a feasible region. What is another kind of a feasible region? Now again, let's look at the function, the same function. Now we see that it enters and never exits the region. So this is another kind of a feasible subset or interval of the generating function. Now, what other types are possible? Let us say we have the same generating function again. And okay, let's look at the function here in yellow, the generating function. We see that the generating function enters it and never exits. However, it also has a tangential point, h, as shown here. And similarly, the curve here in red, it enters and exits. It has an exit point. However, it also has a tangential point. So these are broadly 4 kinds of subsets that are possible inside the feasible region. And the 5th kind is that when it only has tangential point. Yes, that is possible, and that looks like here. If we look at the generating function given here in brown, we see that there's only one intersection point, which is a tangential point. So a feasible subset of SKFF or a feasible region can also consist of only tangential points. So just to let you know that a generating function can enter and exit a feasible region. A generating function can enter and never exit the feasible region, or a generating function can enter and exit a feasible region while having a tangential point. Similarly, it can enter but never exit the feasible region while having a tangential point. And the fifth kind is when there are only tangential points. That's it. So all of these things are shown here graphically. So what are the interesting properties that we get here? We show that whenever a feasible region has a tangential point, whenever, in that case, our trajectory is always going to be circular in nature. Irrespective of whatever f of r we have, it's whenever there is a tangential point, the trajectory is always going to be circular. Now, what is the significance of an entry point and an exit point? An entry point will always correspond to the minimum distance from the target point, and exit point will correspond to the maximum distance from the target point. So let us try to understand physically what these things mean. So in the generating function space, let us say we reach the entry point. Now the entry point in the physical space of an agent would actually correspond to the agent being closest to the target. So it cannot go any more closer. Given the control input, it cannot go any closer to the target. Similarly, an exit point in the generating function would correspond to the point when the generating function actually leaves the feasible region. Now, again, coming back to the real world where the agent is sitting, now this is the farthest that the agent goes from the target. Given the control law, it will not go any farther than this point. So that means entry and exit points actually give us the maximum and minimum distances from the target point. So that means these are actually bounds of the trajectory of the agent that we get. So that means by controlling the entry and exit points, we can actually control how far or close we are going with respect to the target point. All right. Having said that, another interesting thing that we get is, in case we have a generating function, let's look at this curve here in pink. Now, again, what kind of, let's say there are two feasible regions. So we just mentioned that the minimum always corresponds to the entry points. Now we see that here there are two entry points. The first one is A and the second one is C. So which is actually going to be the minimum here? Now the answer to that question is that it depends on the initial conditions. So using Poincaré-Bendixson theorem, we actually prove that the trajectories are always periodic in nature most of the times, and I'll explain when they are not. So, and let's say we choose a certain initial condition such that we are inside the region RA to RB, and which would correspond to this region here. So this would mean that a generating function, so we can, in the generating function space, we keep moving periodically from point A to B to A to B, and this is a periodic motion which keeps happening. So that means if we start inside this region between A to B, we will never cross over to the other feasible region, and vice versa. If our initial conditions are such that we start in this feasible region, which is C to infinity, then we will actually never go to the other feasible region. So that means each of these individual subsets or individual feasible regions are in fact invariant with respect to time. They're positively invariant in the sense that if you start in any one of these subsets or any one of these feasible regions, then you're always constrained to move inside these feasible regions. And not only that, we also prove that, let's say if you have a bounded trajectory where you have an exit point and an entry point, in that case, your trajectory using Poincaré-Bendixson one can show that the trajectory will always be bounded and periodic. So that means the agent will keep going from minimum to maximum, again to minimum to maximum, and that continues. Yeah, this talks about the same aspects. So just to remind you that if we have both entry and exit points, that means we have both an upper and lower bound for R. Similarly, if we do not have an exit point, there's actually no upper bound. That means the agent can keep going far and farther away from the target. And whenever there's a tangential point, our trajectory would always be circular. So here is the main result of the work. Now, in this work, the primary objective or the main idea that we wanted to show is that if we have a unicycle system and some given function, like we are only measuring distance information from a fixed target point. Now, in that case, if we choose the angular rate of rotation of the heading angle, basically, then like with constant speed, we can get only 3 kinds of trajectories using the unicycle. The first one is an annular trajectory, which is also periodic, as shown in the figure here. That means since this is a bounded trajectory, we have a lower bound on R, which is given by the smaller circle here, and an outer bound, which is given by the larger circle here. So because of this, we can say that it has both an entry and an exit point. And the second kind of trajectory is when it does not have an exit point. That means there's only an entry point, and the trajectory can actually increase in an unbounded way, as shown in the spiral trajectory here. And the third kind is a circular trajectory, where the agent keeps moving in a circle, and this happens whenever there's a tangential point. So we show that in this framework, if one can measure only distance information with respect to a target point, then we can get only these 3 kinds of trajectories. Here are just some examples. So we see on the right hand side, we have a bounded and periodic trajectory. So immediately we know that there's an entry point and also an exit point. So when we backtrack it and go to the generating function space, we actually see that we have an entry point and an exit point, and both of them correspond to the maximum and minimum radius of the agent. I'll also show a simulation for an unbounded or spiral-like trajectory. And we see that in the generating function space, there's an entry point, but no exit point. And correspondingly, the trajectory keeps going outward. So this is just an example. Now the user can actually design any kind of trajectory that they want to design by just simply choosing or simply creatively choosing the function f of r. And so we only talk about the bounds, our minimum and our maximum, or entry and exit. So how it moves between these 2 bounds is actually governed by the function f of r. And this is something the user can design. For example, we see that the curve number c is a very dense trajectory. However, the D curve is rather sparse. So depending on the application and by suitably choosing f of r, we can actually control all of these aspects in a trajectory. Now, I mentioned that in practical applications, a very important aspect that we would like to control is the bounds of the trajectory. Now, for example, let us imagine a surveillance applications. Now, in a typical surveillance application, you do not want to, let's say we are all interested in monitoring the boundary or perhaps the entire region, some sort of an annular region or something like that. Then we neither want to move too far away from the target, and we also perhaps don't want to collide with the target point. Let's say if it is a building, so we want to maintain some distance from it and also not go too far away from it. So in those kind of cases, we are actually required to control the maximum and minimum distances from the target point. And this can be done by actually just choosing an entry and exit point. So how would we generate a desired trajectory? So what we do is we go back to the generating function space and we plot some line correspond to the minimum value of r, and another line, let's say, corresponding to the maximum value of R. Now, remember that since we want this to be a minimum points, they must correspond to the entry points of the generating function. That means now we actually put a constraint of on the generating function that they must enter only through the points A or B, such that the entry points correspond to R min. Similarly, the exit point should correspond to the points C and D if you want to fix the maximum value of the radial distance. Now, previously a feasible region consisted of the entire region between the lines plus VR and minus VR. However, in this case now, if we specify the maximum and minimum radius, our feasible region actually shrinks to a trapezium. And this is what it looks like. It should, generating function must only lie in this trapezium. Okay. Now, so we also explored one more idea where we talked about, let's say if you want to, so suppose we want to generate an annular trajectory. Let's look at it through an example. Yeah. So let us say we want to generate an annular trajectory as such, but maybe our initial position of the robot or the agent is placed somewhere not inside the annular region. So in that case, how would we actually reach the annular region and then generate a suitable trajectory? So what we propose to do is, we propose a switching strategy where one switches the generating function only once and starts generating a desired trajectory. So as I mentioned, using this approach, one can generate numerous kinds of trajectories, and by actually finely looking at the function f of r, we can add more and more constraints to the trajectory. For example, even the curvatures. So there are ways to control that as well. Okay, so here are some applications which I'll just talk about in minor details. So let us say we have the first case here. Let's look at the first trajectory. So the first trajectory which is shown here actually shows the case when we want to generate some annular pattern. However, the initial position of the robot is, or the agent, is not in that annular region. So which is practically possible given that, our agents are generally spaced somewhere else. So using this approach, we can still do that by switching the generating function. Now, the second case is something which is known as target switching. Now, instead of switching the generating function, what happens if now we keep changing the location of the target point? So what happens in this case is that we actually keep generating, or we can actually generate boundary surveillance applications for any arbitrary boundary. So this shows an arbitrary boundary, and by simply changing the target locations, we can in fact surveil or monitor the boundary of any arbitrary shape. Now the third case is some sort of a surveillance, let's say, where one has to surveil several regions in a plane. Now, how would one go about doing that? So using this approach, that it is also possible to generate, let's say, two kinds of annular trajectories. For example, let's say first annular trajectory lies in this region, the smaller circle. Now, the second one actually lies in some farther away annular region. So using this approach, by suitably changing the generating functions again, it is possible to generate such trajectories. A very important aspect that we are able to control using in this framework is like we have been able to incorporate the constraint of input saturation in the generating function space. And the way to do that is by controlling the slope of the generating function with respect to R in the generating function itself. If we bound the rate at which G of R changes, then we can actually bound or we can actually control the rate at which omega changes, which actually pertains to the input saturation constraint in the system. Okay, so just to give you some feel that what like all the works that we discussed here can in fact be applicable on a single robot. Let's look at some simulation. Yeah. So the left-hand side is a MATLAB simulation which plots the trajectories and shows how the target is moving. And on the right, we see the target actually generating annular patterns between two different regions. See, now it's switched the annular region, and now it is generating a trajectory along the outer radius. And after some time, we switch such that it enters inside the region. So we'll see that shortly. Yeah, so now the agent started generating smaller trajectories. So like using this approach, we can also create differential surveillance or differentiated surveillance of a region using this kind of a switching strategy. All right. So in order to carry out this implementation, so this was carried out in Systems and Control Engineering Department of IIT Bombay, where we actually, so the system was created by Professor Arpita Sinha's group, where an overhead camera is being used to give us sensory or range information. So we show that, it's so far we talked about a generalized scheme. Now I'll just show if we use a simple, let's say a proportional control scheme where the input is directly proportional to R, how would things look like? So this is just for a simple case, and yeah. So let's say we choose the input to be directly proportional to R, and we call it a proportional control scheme. So in this case, we see that our entry and exit points, like in the generating function space, we will always have an entry and an exit point, implying that our trajectories will always be annular, like which is bounded, and always be periodic as well. So basically all of these trajectories look like hypertrochoidal trajectories, and they can be bounded below and above by a minimum and maximum radius. So we again had chosen a graphical approach to do the analysis and to precisely find out what kind of, so since this is a simpler looking function, we can control a lot of things. We can, so these are some expressions of how to calculate the exact expressions of R maximum and R minimum in this case. So this was again a graphical approach to do that. And these are some kinds of the trajectories that one can generate in this approach. We'll skip these things. And of course, as I mentioned before, primarily we are hoping that, we could perhaps use them for an application. So because of this, we try to bound the maximum and minimum radius, and we finally show that it is possible to do that. It is possible to do that by simply changing the controller parameter eta. Okay, now I'll just conclude the talk. So what did we see in this talk? We actually saw a unicycle agent in a constrained framework where it could only measure range information with respect to some target point. We showed that in this approach, only three broad kinds of trajectories can be generated, and which are in fact all the feasible trajectories. So there can be no trajectory which is different from any of these three kinds of trajectories. So we could arrive at a complete characterization of the trajectories, and we could also find conditions on how to bound these trajectories, how to incorporate input saturation into these trajectories, and how to control the shapes of these trajectories. And we also showed some ways to, for example, let's talking about the boundary surveillance application where we do a switching kind of a framework, a target switching framework, perhaps a generating function switching framework. So we can also do those kind of things and generate more feasible trajectories, which could be better applicable for practical results. And we saw some hardware implementation where we actually saw a robot implementing these strategies, implying that whatever we are talking about here can actually see the light of the day and is implementable. Okay. So I'd like to thank everyone for listening to me, and I'm happy to answer any questions.
Hello, madam.
Hello.
Yeah, I would like to know, you have pointed out input saturation.
Right.
In those figures that patterns you have shown,
Mm-hmm.
could you please highlight the importance of input saturation?
Highlight the importance, or do you want to ask how input saturation comes into picture in these
Yeah,
trajectories?
yeah, yeah, exactly. How exactly that is with respect to the uh, figures that you have already shown in
Right.
explaining,
So,
just
right.
yeah, effect of that input saturation.
Sure, sure, sure. So, actually, I haven't really included any slides on that here. So, so this, what we see here, let me go to the, perhaps you're referring to this.
Yes, yes.
Okay, so in this, we haven't exactly, so I haven't added the figures here yet, but in one of our conference papers, we incorporated input saturation. And so what we can actually do is if we incorporate input saturation, then our trajectories go a slightly flatter. For example, like the figure D.
Okay.
Yeah, so this is how it manifests in terms of the trajectories. So it will still be annular and periodic. Let's say if it is
Yeah,
already doing
yeah.
that.
Now, yeah. Now it's clear. It's clear.
Yeah.
It's clear. Yeah.
Okay,
Thank you.
no problem.
Hi, Twinkle.
Hello.
Hi. Okay. So this is Lalpriya.
Hello.
Hello. How are you?
I'm good. How are you?
I'm fine. Okay.
Okay.
Okay, Twinkle. I just have a question for you. Like the control concepts, no? Did you actually use the proportional control for all of those schemes which you had done in that 2018 paper also?
No, so the 2018 paper included only like the generalized case.
So
So
like the
first we started working with a proportional control scheme, and later on we decided to generalize it.
okay. So generalized means like what type of control was that?
So it's, you see, it's like any f of r. So if the input is any f of r, implying that, one could simply choose anything that they want. So the idea was to see what all trajectories are actually possible to generate using a unicycle if we have if we have constraints on the sensing capabilities.
Okay. So it's like any non-linear control would also be fine, right?
Right. Okay. So this is the guidance part of it. So, for example, when I talked about, let me show you the hardware implementation on a robot. Wait a minute here. Are you able to see the screen?
Yeah, yeah. I
Yeah.
can.
So if you see that there are two dots here.
Yes.
So basically, when we want to so these are just guidance algorithms. Now, when we want to implement it on a real world system, we will definitely need a control strategy.
Yes.
So what we have done here is a leader follower kind of approach to implement it.
Okay.
So actually control comes in there. Yeah,
Okay. Okay. All right. Thank you. Thank you, Twinkle.
no problem. Okay, so if there are no further questions, then I'll take a leave and thank you for having me and listening to me. Okay, thank you.
Hello. Hi all. Hi all. Am I audible?
Yes, Dimya, you're audible.
Today we got an eminent person in the area of guidance and control. Thank you, ma'am. Thank you for your great presentation. The session was very informative. You explained very well about the generation of feasible trajectories and the characterization of agent trajectories for the generalized control input. It was a nice talk. So, on behalf of GEC Thrissur, AAA department, and all the participants, I extend our thanks to you. Thank you, ma'am.
The participants will join back at 11:30.
Good morning, ma'am.
Yes, yes, good morning.
How are you? We had met for the last course also, Uma.
Yes, yes, I have attended physically. I think in the year of 2017, I went. Yes.
Yeah, right. Okay, so shall we start?
Yes, yes. I'm ready. If your audiences are ready, then I can start.
Okay. Okay, so welcome back, participants. So for this session, we have with us Dr. Manas Kumar Bera, and he will be engaging on a topic, event triggered control. Dr. Manas Kumar Bera is working as an assistant professor in the Department of Electronics and Instrumentation Engineering, National Institute of Technology, Silchar. He received his PhD degree from Indian Institute of Technology, Bombay. Completed master's degree in control system engineering from Jadavpur University and BE from the University of Burdwan. He has authored and co-authored several books, journal papers, and has been referred to several journals and conferences. His current area of interest includes control theory and its applications, biomedical application of control, multi-rate output feedback, continuous and discrete time sliding mode control, higher order sliding mode control, adaptive control, event triggered control, etc. So we have this eminent personality with us today. On behalf of Department of EEE, GC Trishur, and all the participants, we welcome you, sir, to this session. Thank you.
Yeah, thank you, madam, for warm welcome. And I am delighted to deliver a lecture in this platform. And without spending much time, let us start the topic. Am I audible? Is it fine? My voice is okay? Yes, okay.
Yes.
Okay, so you see the network connectivity is fragile. So if anyway, if I am disconnected, please, I have mobile with me. So you can call or give a WhatsApp message such that I will be aware that whether I am connected or if I am disconnected. Okay, so let me share my screen. Okay. So my screen is visible?
Yes.
Okay. So as Madam has already introduced that today we are going to talk about event triggered control paradigm. Maybe the first, Uma Madam, can you, yes. Can you switch off your microphone? Yes. Yeah. Okay. So today we are going to talk about, or we are going to discuss about the event triggered control paradigm. And I want to keep this discussion very simple such that those who are planning to start their research or planning to motivate his or her student to start this research, then it will be useful for them. So I will start with the basic concept such that you can understand that why the event triggered control nowadays become a very popular control technique in the area of network control system or the event that is Internet of Things and many more. And now these are my outline of presentation, introduction. Then I will discuss that why the event-based paradigm is so important, why it has evolved over the time. Then little bit of Lyapunov's stability theory we will recall such that we can understand the two motivating examples. These are mainly the academic examples I will cite, and then at last I will conclude with the basic event triggered control setup with some references. So I will start with very familiar block diagram of a classical digital control system. Maybe those who are involved in teaching of digital control theory as well as the classical control theory, they may be knowing this block diagram. So this is the block diagram of classical digital control system, where you can see that the process, the output of the process is measured by sensor. And now here we want to use the computer or the microprocessor as a controller. So that's why we need to sample the measured signal. So here you can see that the measured signal or output YT is measured, and then it is sampled at a regular interval of time, or periodically we will say. So periodically this YT is sampled. So sampled version of the measurement signal is Y of K, and that measured signal is given to the controller. So the controller having some algorithm, maybe PI, PID, or any other modern algorithm also. So then based on this measured signal and the control algorithm, controller is going to produce the control action at kth instant of time, so UK. Now most of the actuators, you know that they receive the continuous signal UT. Then we will use the hold circuit to convert this discrete signal to the continuous one, such that whatever the control action has been produced, that can be executed through the actuator to achieve the desired result. So this is a very familiar setup, we already know. But most important thing here is to be note down is that here this sampler and the controller, they are updated. Means I want to mean that the sampler is going to take the sample at kth instant of time, and the controller is also updated at kth instant of time. So this the updatation of the controller and the taking the measurement of the sampled signal are governed by a clock. And once you will set that what will be the sampling time for this control system, all the future sequences of sampling instances are known to you. What is the meaning of that? Means if suppose you have decided that I want to take the sample at 1 second interval of time, then all the future sequences of sampling instances are known. So this is the basic setup for a classical digital control system that we are knowing. And that has been discussed in this slide. So in today's standard textbooks, periodic control is presented as the only choice for implementing feedback control laws on digital platform. Now, here in this slide, you can see that the signals associated with different stages for a classical periodic sample data control system. Here you see YT is an analog signal. Now it has to be sampled at a regular interval of time. So this suppose if the T1 is known, then T2, T3, all the future sequences are known to you, and then at the same periodic interval of time, we are going to update the control law, and with the whole circuit we are making it continuous to give it to the plant. So this is very well known control theory we are habituated to know. Now some observation now in this stage is required for this classical digital control system. What are those observations? The computer control system have been widely used these days due to the numerous advantage where the control is updated in we are sending the measured signal to the controller, and control signal is sent to the actuator through a single dedicated channel. We are not using this is the information through this channel it is going. Suppose if it is a wired control system, then we are using that particular channel, where channel to send the measured signal. Let me see, is there any difficulty? Okay, no, fine. Okay, so what I'm discussing, that now this is a dedicated channel is used to send the measurement signal to the controller, and the control, after computation, controller is sending the control signal through a dedicated channel. So this is the one of the most important observation for this classical digital control system, you can say. And next thing is that in classical control implementation, the reduced time sharing capability of the digital processor is always been an important concern, which can make the processor to work in multitask environment. Means here the controller what we are using, maybe it is embedded system, and that embedded system or the microprocessor, it is not necessary that it will be used only to control this plant. It may be used for other purposes also. Okay, so because we want to explore the multitasking capability of this embedded system or the microprocessor. So that is another observation we can have with this classical control system. So it is always desirable to minimize the number of control update in digital implementation by limiting the sensor and control computation to only when the system need attention. So this is the point, very important conclusion, or you can say that the desired features we are expecting from a control system. What is that? You see in this setup, we are going to sample at periodically. So now what will happen? The controller has to be updated also periodically. Means controller is going to compute the control signal periodically based on the measurement signal what you are providing to the controller. Now every time the controller is engaged, whether it is needed or not, the controller is going to compute the control signal. What is the meaning of whether it is needed or not? I want to mean that suppose your plant has achieved the steady state response, whatever the response you are expecting from the plant, it is achieved. When it is achieved, then also you will find that the measurement signal is going to be updated, and the controller is going to compute the control signal at that time also, whenever it is not needed. So that's why, can we think an alternative such that we can release this controller or embedded system or microprocessor for other tasks, if only when is required to compute the control signal for the plant, then only we will do. Otherwise the controller as well as the channel will be free for the use of other purposes. So that with that motivation, okay, with that motivation, we will move towards the alternative. But before that, this claim that whether we can go for any alternative where we can update the control signal or we can compute the control signal as when required, okay, need based control strategy or control update, whether we can do or not, this claim will be more supported by this observation also. That what is that observation? From a purely theoretical perspective, executing control tasks in a periodic fashion seems unnatural and inconsiderate to the dynamics. Okay, we will establish that from the theory point of view also, the periodic manner whenever you are executing the control task, it is actually not the natural one. Natural one is you update the control signal whenever the system needs attention. And even we accept the periodic paradigm, it is unsettling that we still do not understand how the sampling or execution period should be chosen. That is also a very interesting question to be put, that even if we are favor of utilizing the periodic implementation of the control law, but how to choose the sampling period for a periodic execution of the control law, that is also unanswered. Why? I will, in support of that, I will I will discuss one very important chapter from a IEEE Control System magazine. It was published in 2007, where a column is there that asks the expert. So what is the question has been asked by a reader? Reader has asked that at my first assignment as a control engineer, my supervisor has tasked me with developing specifications for a digital control system. Do you have any advice on how I should select the sampling frequency? So this has been asked by a reader, and the answer of this question is given by a very famous control engineer, G.F. Franklin. Maybe you have read the book of Franklin Powell. So he is giving the answer. Just you follow what the answer he is giving. He is giving the answer that in general, overall system performance and budgets press to push control engineer to set as low a sampling rate as possible. Within this environment, the following three rules guide sample rate selection. What are they? First, it's sample as fast as project managers, technology, and money permit. Okay. Second point, he is telling that follow the guidelines given in the standard textbooks of this Franklin Powell, where he has given some idea on based on the time constant of the system, some thumb rule he has given how to select the sampling frequency for a given digital control system. Select a reasonable rate and explore other choices by simulation. And why I have taken this example, because you see all these three answers is not very concrete. Okay, so all these answers are philosophical, and based on the system to system, your requirement is going to change. So now, even if you are stick that I'm going for the periodically updating the control law, or periodically going to sample the measurement signal, at that case also you are not sure that what should be the sampling frequency has to be chosen. So in this situation, to claim our requirement, or to strengthen our requirement that we want to switch from the periodic updatation of the control law or periodic sampling, we want to switch the sampling which is need based. To on support of that, we will see that network structure of the network control system in contrast to the classical control system. Because nowadays you will find that we are moving towards the network control system, then Internet of Things. All these paradigms are very important, because nowadays we are more focusing on these kind of systems, because internet become essential, or the network become very much essential in our day-to-day life. Now, if we are talking about the network control system, the network control system is completely different. Its architecture is completely different from the classical control system. How it is different? Now you see here plant, everything, plant controller, then hold actuators, all this is same. But now you see whatever the measured signal YT we are intended to send to the controller, not through a dedicated channel. You have to send it through a communication network, and most important feature of this communication network is that it is shared with others. Okay, so this communication channel is not dedicated to this control system only. In case of network control system, this dedicated channel is shared for other purposes also. Okay, and now the controller, after receiving this signal y of k, that is the output signal or the state from the plant, the controller, after computation, whatever the signal uk control signal has been generated, for that also we are not following a dedicated path. We have to send it through a shared communication channel, digital communication channel. So that is the main architectural difference between the classical control system and the network control system. Now we have several advantages of this structure, but now here we want to focus, if we are not using any reliable dedicated channel to send the measured signal to the controller and the control signal to the plant, then what are the challenges we have to face? That is very important to understand when we are moving towards the network control system. The challenges are that with the advent of network embedded control system, we can no longer rely on the assumption of dedicated hardware or dedicated channel for communication. Means here the hardware what you are using, okay, that the controller may be, okay, or the embedded system what we are using here, so they can be they may be shared with other purposes also along with the communication network. Along with that, other problem or other important features of the network control system is that embedded systems are characterized by reduced computing and communicating capabilities, and available power is limited and has to be carefully managed. Basically, we want to mean that the challenge of NCs is that it is a resource constraint application. Okay, why? Because here power are also because suppose you are using a wireless network. So now the measurement system, controller where you have implemented and the actuators, all they are battery powered. If it is battery powered, then every time you are busy with calculating or sending the data as well as you are updating the control signal, then what will happen? The energy consumption will be more, and then this kind of periodic control updatation or periodic signal means what periodically if you measure the signal and if you send it to the controller, it may be wastage of not only the battery power but also the network resources like bandwidth, and with that the computational resources also. So this is basically I wanted to emphasize that in this situation we need to design the theory of integrating control, computation and communication. So 3 C's are very important. Control in case of network control system or the Internet of Things, you will find that this control, computation and communication, these 3 things has to be integrated such that we can manage or we can accept the challenges put through the NCS. Okay. Now, in this situation, our objective is to reduce the rate of message transfer through the shared communication channel to reduce the communication burden. So we have to develop a mechanism such that we can reduce the rate of message transfer. Means whenever is required, then only we are going to send the measurement signal, otherwise not. And if you do this, then we will get several advantage. Why? Now you are not using the communication channel frequently. If you are not using the communication channel frequently, then you are saving the network resources basically. And also this will minimize the power consumption in wireless communication. And on the other hand, the reduction of communication traffic, if you send the messages as rarely as possible, then the network channel will be free. But unnecessarily, periodically, if you are going to send the data through the communication channel, then what will happen that the whole system will be affected by the adverse effect of network induced imperfections. So what are the network induced imperfections? They are the delay, packet jitter, packet losses, all these issues will be there. So this can be avoided if you are going to use the computational facilities or computational resources or the communication resources as rarely as possible. We have to develop that kind of system, and the hardware and communication network must be released for other tasks. That is very important. If as rarely as possible you are going to use the computational facilities and the communication network, then it can be released for other tasks also. And that is the benefit of, you can say that, or that is the requirement of network control system, you can say. And the hardware like sensor, actuators and controllers in a network control system loop, what you are using, that should be used only if necessary to save energy in battery powered equipment. Okay. So now in this respect, if you relook the classical sample data control system once again, that whether they are fit for this situation or not, then you will find that they are not fit, because the measured output signal is sampled periodically according to a fixed sampling rate. Okay, you do not have any control over that. So periodically you have to send data, and controller is also periodically updated. And the periodic sample data paradigm evolves according to a certain clock sequences, because it is governed by the clock sequences with an equal time distance between two consecutive clock instances. And once the sampling rates are determined, all future sampling instances are known, and the sampling action is performed along the horizontal axis, that is known as remain sampling, and it is projected here. You see, if you assume that this is analog signal and the sampling is governed by the time axis, once this capital T is fixed, then you know all the future sequences of sampling, and the sampling is governed by the clock, that you if the Ti is known or Tk is known, then the next sampling instant Tk plus 1 is also known to you for this the periodic sampling. And also the T, that is capital T, that is period, that is Tk plus 1 minus Tk, is also fixed. So now in this situation we are telling that this kind of sampling technique is ineffective in the use in the scenario of resource constraint situation like network control system or Internet of Things structures. Okay, so and our claim is that actually we are doing unnecessary computational control updates even when there is no demand. So now in this situation, once again we will know that what is the demand of NCS, network control system. The demand is that the effective utilization of communication, computing and energy capabilities, and the economic use of computational communication resources, and we should provide ubiquitous wireless connectivity between smart devices with the energy. We know that in that situation energy resources are not sufficient, and it poses a requirement to manage efficiently the constant energy budget. So this is the requirement of the NCS. We have to develop a strategy where we can meet this demand. Now we have to think what will be the alternative of this, that periodic sampling and the periodic computation of the control signal. What should be the alternative? The solution may be that the solution maybe means we have to think in this way, that then when to sample. If we are not allowed to sample periodically, then when to sample, when to update our control action, and when to transmit the information. And to answer of this question is roughly given in the figure. How you see, suppose this is a typical evolution of a measured signal, suppose x of t. Okay, and now we have decided that we have decided a band. Okay, we have decided a band. Suppose this band is defined by E. Okay, defined by E, and our intention is that whenever this trajectory will be inside this band, then we are not going to take the sample, and whenever this condition is going to be violated, then only we are going to take the sample. So now it is a need-based sampling strategy. We are not going to be forced to take the sample with respect to time or by the clock. Rather, we are forced to take the sample by a occurrence of an event. You see, at the tk we have taken a sample x of tk, but whenever the system trajectory is going to be inside this band, we are not interested to take the sample. We are taking the sample at tk plus 1, because at that time it is going to violate this condition. Okay, where xt is the current state and xtk is the last measured state. And now the question is that how we will decide this event based on which the triggering will be done. Then how we are going to decide this event, that we are going to discuss definitely in the consequently. Okay, so now that's why here in this situation the alternative approach we are claiming that that we will go for the event-based sampling or event-based paradigm. In event-triggered control framework, the necessary sampling or communication is determined by the occurrence of an event rather than the time. Okay, and you will find that due to the nature of this sampling, that it can save the energy, it can save the computational resources, and it can save the communication resources, and that's why it having large application in the network control system, Internet of Things, and cyber physical systems. So the event-driven control is closer in nature to way a human behaves as a controller. If you see, the decision taken by the human is not actually the time-driven, it is actually event-driven. I can give you an example. That's why I told that the periodic sampling is not closer to the nature. Rather, the event-triggered control or event decision taken by the event is more closer to the nature. Suppose one example I'm giving. Suppose manually this man or this person is going to control the level inside the tank. Okay, so do you think that this person is always or continuously monitoring the level of the tank and continuously going to actuate this valve? No, it is not true. This person is going to actuate this valve only when he is observing that the level of the water is going beyond a threshold value. So you see, you are going to decide about the actuation of this control valve only when there is a occurrence of an event, and this event is set by your mind that okay, or by your design that okay, I am going to actuate or close the control valve only when the water level is going to exceed a threshold value. So this control, manual control, is not the time driven. Instead of that, our decision is based on event. Okay. So in this situation, our talk will be based on that abandon the periodic paradigm in favor of the event triggered control. And the reason is very clear. In the context of sensor actuator networks, we would like to execute control tasks as rarely as possible, means whenever required, only we are going to take the measurement signal, or we are going to send the, or we are going to sample the measured signal, and that signal we are going to send the controller, and then only the controller is going to be updated to take the corrective action. Okay. And if you do that, we would like to execute the control task as rarely as possible in order to minimize the energy consumption due to communication. And even if energy is not concerned, the less often control tasks are executed, then the processor time is available for other important tasks. We will free the processor, means even if you are not engaging the controller or the processor every time, then the controller will be free to explore the other multitasking activities. Okay, so this we want to achieve without compromising the system stability and performance. This is a very important thing, that okay, somebody can say that okay, we can go for the event-based sampling, then what is the big deal? Big deal is that we are very much satisfied with the periodic implementation of the control or classical periodic control, where we are going to achieve the system stability easily, and also because mature theory is there, how to ensure the stability as well as how to design the controller to achieve the desired performance of the system. But here we want to achieve the same system stability as well as performance, but taking the sampling as rarely as possible. That is our objective basically. Okay, so now in comparison to the classical control theory, if you see the event-based control, then you will find that some of the extra things you will notice. You will find that with the plant we are using a block called event generator. Okay, the work of the event, you can think it is a smart sensor also. It is not only measuring the state or output of the plant, along with that it is going to take or it having some computational facility. What are the computational facility it having? Now, it is continuously monitoring the output of the plant or the state of the plant, and based on some condition, it is going to evaluate some condition continuously to decide when to take sample. It is going to decide that TK instant of time. Okay, once it is going to decide that, okay, this is the moment the sampling has to be taken, then that sampled version of this output or the state is going to be sent through the communication network to the controller, and at that moment only the controller is going to be updated at TK instant of time, and then that control action is going to be sent through the plant through a smart actuator. Because why it is called smart actuator? It having some computational facility, that is TK means it is going to convert the UTK to UT such that plant can accept the continuous input. So this is the whole setup, basic setup of event-based control loop, you can say. Okay. So here some discussion has been given. What is the work of event generator? What is the work of the controller? And what is the control input generator is doing? Okay, so this thing has been discussed. And now in comparison to the classical digital control system, if you see the event-based control loop in terms of signals, then you will find that we are not going to take the sample of the measured signal periodically. Instead of that, whenever the event trigger or event that is event trigger generator, you see event generator is going to instruct that, okay, now the sample has to be taken, only that moment the sample is taken, and then the controller is updated. You see, it is not updated periodically, and then whole device is going to convert it to a continuous signal to the plant. So this is the signal associated with the basic event-based control loop. And more it will be clear if you compare these two figures, where actually we are showing the periodic versus event triggering sampling. You see, first the signal, a arbitrary signal has been taken, and we have said that at every 1 second interval of time, suppose we are going to, or 1 unit of time, we are going to take the sample. So every periodically we are going to take sample x0, x1, x2, x3, x4, x5, x6 at 0, 1, 2, 3, 4, 5, 6. Okay. But in case of event-based sampling, you see, we have decided that whenever the analog signal will be inside this band, we are not going to take the sample. Okay. And whenever it is going to exceed this band, then only we are going to take the sample. So now this sampling is governed by an event or condition. Whenever it is going to outside of this band, only that moment of time we are going to take the sample, otherwise not. So it is a time triggered sampling, and we can say this is an event based sampling. Okay. Now, in summary, we can say that the event-based sampling is a aperiodic implementation of control strategy with the event-based sampling, and sensor sampling and control actuation instance are generated when the plant state deviates a certain threshold from a desired value. And in this technique, essentially a stabilizing, that we are going to understand that how actually we are going to evaluate the event condition for a dynamic system, that we are going to see. And basically you will find that that is a stabilizing condition is maintained such that the application of the control signal at certain time instance known as triggering instance to the plants ensure the desired stability or performance. And the triggering rule or the event governs the control update, and sampling action is performed along the vertical axis. Previously, for the periodic sampling action is performed by time axis, means that is the horizontal axis, but now the sampling action will be along the vertical axis, which is known as Lebesgue sampling. So here you see sampling now is based on not time, based on xt. If we put a condition on xt, that okay, if the xt is going to exceed some threshold value, then only we are going to take sample. So that's why the event triggered control system, you will find that not the tk plus 1 is not determined by the clock. Instead of that, it is determined by an event, and as a control engineer you have to design this event. Okay, and that will depends on a stabilizing condition. Basically, when I will give an example, that time it will be clear triggered control system such that we can ensure that the required performance and stability, and along with the sampling, we will take as rarely as possible, or as when as required. Okay, so then definitely somebody can ask that what is the new with event-based control. Now, in sample data control theory is no longer applicable because it is fundamental assumption of a periodic sampling is violated. You see, previously, suppose if the system is given in discrete domain, that is x of k plus 1, suppose a into x of k plus b into u of k, and suppose you have decided that that the control also will be updated periodically, so then u of k, suppose k into x of k, state feedback control law. So then if you substitute here, then the closed loop system x of k plus 1 can be easily represented, that is a minus bk of xk, and then you can design this k to place the poles of the closed loop system at the desired location. It is very easy to represent the closed loop system when your sampling is done periodically. And now that theory cannot be applied directly to this event-based sampling control. Why? Now, as the sampling time is not predictable, because you do not know, suppose now tk instead of time, one sample has been taken, but tk plus 1 is not known to you. Okay, but tk plus 1 will depend on the condition when it is going to be violated in a closed loop system. So that's why it is not, it cannot be predictable. So as the sampling time is not predictable and the sampling frequency changes from one event to the next, there is no chance to represent the planned behavior at the sampling instances in a compact form, as we have done now, as in the sample data control theory. And the continuous time here, the plant will be in continuous time, and you are doing all the sampling as well as the computation of the control law at discrete event of time. So that's why it can be modeled as a hybrid dynamical system, and which leads to a complex analysis and design task. Okay, so the complexities are increased in the event-based implementation as the inter-sampling behavior of the set trajectory determines the sampling instant for applying the control input. Okay, that we will see definitely. So fundamental question rises that when should information be transmitted from the sensors via controller toward the actuators, that we need to be specified now by the design. And how should the control input be generated between two consecutive event instances? And moreover, most important thing is that which improvements can be obtained by event-based control in comparison to periodic sample data control with respect to an effective operation of all components in the loop. So that is the most important thing. Okay, we are adding complexity, everything, but what benefit we are getting out of that, that need to be ensured when you are going for event triggered control in comparison to the periodic control or periodic implementation of the control strategy. So that need to be, so actually I am telling that how when someone is going to research on this event triggered control system, then what are the things actually needed to be addressed when we are going to develop a event based control strategy for a control for a system. Okay, so so this is I think up to this the philosophy behind the event based control is clear. Now I will take question after my presentation, and then if you can note down that what are the queries you have, then I can answer if possible at that moment of time. Now if we want to answer all this question, that when to be transmitted and what benefit we will get out of the implementation of event triggered control system, we will just look on the Lyapunov theory. Just we will revise that concept. I'm just skipping this part because this part is known to you. That suppose we have a nonlinear system that is x dot equal to fx, okay, and x0 is the initial condition is x naught, and it having n number of states or having n number of components. It is a Rn space. So, so D is an open set which consists actually 0. We are assuming that 0 is the equilibrium point, and now we want to ensure that whether 0 is the stable equilibrium point or not. And even if it is a stable, then what kind of stable it is? Is it asymptotically stable, or is it exponentially stable, or it is globally asymptotically stable, or it is globally exponentially stable? That thing we want to discuss. But I'm not going to give an idea of that, but better that just to revise it, that what the Lyapunov stability theorem definition is saying. It is saying that a equilibrium point is stable in the sense of Lyapunov, and 0 is the equilibrium point, is stable in the sense of Lyapunov if for each epsilon greater than or equal to 0 there exists a delta which is also a positive quantity, such that norm of x0 less than delta implies norm of xt also will be less than epsilon. What is the how we can interpret this result? Result is like this, that some challenger has come, and challenger is some person is a challenger. He is or she is asking that he or she has given a epsilon, and telling that, can you guarantee that all the future trajectories of the dynamical system will be inside the ball with a radius epsilon? Okay, now the phasor after some calculation is telling that yes, you take this delta and start from that delta. You see, x0 means that initially if you able to start inside a delta ball, then we can ensure that all future trajectories of the system is going to be evolved inside the epsilon ball. So this is the interpretation of the Lyapunov stability theory. Okay, and now different definitions are there, but most important thing is that this is the Lyapunov stability theory. That was the definition. This theory is known to you, but most important thing here, I want to focus the stability of a Platov system. That is very important to understand. Maybe all of us is knowing that the system that is x dot equal to fx, the stability of that, but what will be the stability if a perturbation term is there with the system? Then how we can ensure the stability? Now the perturbation term G could result from modeling errors, aging, uncertainties, and disturbances which exist in any realistic problem. And in a typical situation, we do not know the G, but we know some of the information about it, like we can have the knowledge of upper bound of G. And if we will assume that G is a non-vanishing disturbance, it means that even if the states are going to converge to the origin, the G is not going to be 0. If that kind of disturbance is there, then we cannot ensure the stability of the origin as an equilibrium point, or nor we should expect that the solution of this Platov system is approached to the origin as t tends to infinity. So if we are going to consider the stability of a Platov system, we cannot ensure that one. So instead of that, what best we can ensure? Now the best we can hope for that, the perturbation term G is small in some sense, then xt will be ultimately bounded by a small bound. That is, norm of xt is not going to converge to 0 as t tends to infinity. It will be ultimately bounded by a region. Okay, and that leads to a definition of the stability called the ultimate boundness, or which is known as practical stability. Basically, why we wanted to focus on this practical stability, because using event-based control, we can ensure the practical stability of the system. And that's why when we will say that the system is practically stable, the same thing, can we ensure that xt will be inside a ball that is, or inside a region that is capital gamma d, sorry, not gamma, it is a omega, capital omega d. Now we are telling that yes, it can be ensured, and it the trajectories are going to enter to this region that is capital gamma d in finite time, if we are going to start from a region that is gamma omega 1. And once this trajectory is going to enter this omega d, then it is not going to leave that region, and it is called robust positively invariant set. And this has to be done in finite time. Finite time it should enter to that region. So this is the definition of the ultimate boundedness of the system. And here another the same thing has been told in this definition also. I'm not going to discuss that one now, because as the time is limited. So now we are going to discuss some of the motivating example, because this is very important to understand any theory. That is that how the design can be done for a system with event-based sampling. That is very interesting to know, and how we are going to ensure the stability and what are the benefits we are going to get out of that. Okay, that is interesting to know. Okay. Okay, so now to do that one, we are going to discuss about two examples: an event-driven PI controller for set point tracking, okay, and another is the event-driven PID controller with the aim of velocity tracking for a DC motor, and which is a very well-known situation. You know, most of the time we are going to teach this kind of problem, that the PID controller, design of PID controller for the velocity tracking of a DC motor. So this is two academic example, very that is very easy to understand. That's why I have taken these two examples from a particular paper, basically. Okay, so the first motivating example, that how we can design an event-driven PI controller for a given system. Suppose we have taken a system x dot, a scalar system, we have taken a scalar plant x dot t equal to a into xt plus b into ut plus a disturbance dt, and the initial condition x of 0 is x naught, and the output is the state, that xt. So we can measure the output xt. So where xt denotes the state of the plant with initial state x naught, and ut is the input, and dt is the unknown disturbance which is assumed to be bounded. So here this disturbance is unknown, but we know that the disturbance is bounded by dmax. Okay. Moreover, the output yt is assumed to be given by the plant xt, means the output means the only state of the system is measurable. Okay. Now, what is our objective? That actually need to be clear. The objective is that we have to design a PI controller which will guarantee the set point tracking. Suppose W is a set point and YT is the output or the state, you can say. For this case, the output should follow this reference input at t tends to infinity, means the difference between the reference signal and the output signal should become 0. And for this particular problem, we have taken a constant reference signal, that is W bar, which is also bounded. We know the maximum bound of the reference signal. And now we have proposed a PI controller. Here CT, you see here I have written x dot CTI. So CT indicates continuous time, I is the integral controller. Okay. So then we have taken a state that is xti dot is equal to yt minus wt. Okay. So basically it is, you can say that it is E dot. Okay. The difference between yt and wt. And now the control law ut can be written ki, the integral gain, into x ctit. That is the solution of this. Means how we will get the solution, that is integration 0 to t, that is wt minus y minus w dt. So basically that is ki into integration of et dt, you can say, and plus the p term is there, kp into yt minus wt. So this is represented as a control law, which is the PI controller. Okay. Now the question is that when in a system disturbance is there, with the PI controller, it is very difficult to ensure that we will have a perfect tracking. It is very difficult to ensure, because we know that PI controller in that sense it is not a robust controller. Okay. So that's why we have to relax our control objective. So we have relaxed here the control objective. That's why it is written control objective is reformulated. Why it is reformulated? Because as we have seen that it is not, we are not with the PI controller, we will not able to guarantee that perfectly the error, tracking error will be equal to 0 as t tends to infinity when the disturbance is present. So instead of that, we have reformulated our control objective like this, that instead of yt minus rt or wt is equal to 0, we want that yt will reach in and around a region defined by the user, and that region will be in and around of w bar. Means if this is the set point, w bar is a set point, then we will define a region and we want to be inside that region. So that's why where omega y w bar is the set of acceptable output values around the desired set point w bar, instead of reaching exactly at the w bar, we want to reach in and around of the w bar. So that's why the term yt minus omega y w bar denotes the distance between the output yt and the set according to this relation 11. Okay. And now with this control, you see the control is defined by 7 and 8, and the system is 4 and 5. And suppose this ut is applied, what we have defined, ut is applied, and now we want to write the closed loop system. And if you write the closed loop system will look like this. Here, two states will be there. One is the system state, ct is the continuous time, and it is the state of the controller. And then we have defined in the term of ai into x plus fi into wt, ei into dt. And these are the initial conditions, because here integral controller we are using, and we have assumed that the initial condition for the system is x0, and for the controller it is 0. Okay, and output equation yt equal to xt, because controller state is not our output, so that's why it is 0. So it is written in a closed loop form. And now the question is that what should be this kp and ki? Question is that what should be this kp and ki such that we can ensure the stability. Means if we able to ensure the stability, then only we can ensure the tracking performance. And this design, what I am telling, this design is not for the event-based design. This design is the continuous time design, simple. Okay. So first of all, we have to know that what is the condition, or whether the controller which is designed in continuous time is going to ensure the stability or not. Okay, that we have to know. And now with this, how we can ensure the stability. Now the definition of the ultimately boundedness, what I have discussed, that will come into play, because you see here two exogenous signals are there, dt, that is the disturbance, and also the reference input wt. In the presence of this exogenous signal, you have to establish the stability of the system, and the boundedness of the system trajectory is guaranteed only when this dt and wt is bounded. That's why the assumption of dt and wt is required. So that's why here we are telling that this system will be globally uniformly ultimately bounded, that the solution x sub ct, that is the system state of the continuous time pi control, is globally uniformly ultimately bounded if for any initial condition of the system, that is xct 0, there exists a positive scalar p, such that we can always guarantee that in finite time this the modulus of xct will be less than equal to p, means always it will be bounded. And that can be ensured if the ai is Hurwitz, this matrix is Hurwitz, and along with that this dt and wt is bounded. Okay, and what is the condition for the Hurwitzness of this A matrix? That can be very easily calculated, and this is the condition. This is the condition A plus B kp less than 0 is the condition, and this condition will ensure that with this continuous time PI control loop, this system will be globally uniformly ultimately bounded. And now we are interested to convert or to redesign this control system in a event based framework. Okay, so that's why here same PI controller, but we want to design an event generator by which similar performance we can achieve, by which the continuous time controller is giving, but here now we want to achieve with a event based strategy. To do that one, what you have to do, that is that this section, that is event triggered PI controller design, firstly investigates the event triggered PI control loop. The main difference to the continuous time PI control loop is that the controller gets new information about the planned output YT only at the occurrence of event, that is at TK instant of time. Okay, and that's why now in the time interval of TK to TK plus 1, we have rewritten the controller equation, that is yx dot, so that's why here CT we have removed. Now if the xi only if it is written, then this is the controller state, you can say in event based strategy. So so we will evaluate this at TK to TK plus 1 when y of TK is the sampled version of state at TK instant of time. Okay, so now with this definitely there will be a error, because you see we are going to take the sample at y of TK, and this is the continuous signal, and the difference between these two we have indicated by a error term ET. Okay, and now we have rewritten the controller equation with this error term ET, and now the controller will look like this, that with this error the controller will look like this. And with this again we will apply this control to the system, and if we will apply, then you will find that the closed loop system will be look like this. The same AI matrix, same Fi, same EI, but now you will find that another additional term has appeared, that is GI. So now if we want to stabilize this system with the event based control, then this ET must be bounded, and this is the clue to have the event triggered rule. So if somehow if we able to some rule by some, that's why I told that event condition is basically a stabilizing rule. So if we some condition we are able to introduce, by which if we able to ensure that ET is bounded, then that will be the stabilizing condition. Okay, so if we will find that the stabilizing condition means ET, a stabilizing condition with ET we will find out, and if it is going to be violated, then only we will take the sample, otherwise we will be we are not going to take the sample. So that's why how to define the event condition. To prove the stability and the set point tracking property of the event triggered control loop, the output error, that is the YT minus YTK, has to be bounded, and that condition ET YT minus YTK E bar has been taken as a stabilizing condition or event condition. Means if we are going to exceed the E bar, then only we will take the sample, otherwise we are not going to take the sample if we are inside the error defined by the designer. And definitely this is going to give you the that planned state. You can guarantee that it will be globally uniformly bounded. For that you can define the condition, and also you will be with this also you can ensure that you are not going to deviate from the desired trajectory. You will be ensured inside the means in and around the trajectory, and also you can guarantee that minimum inter-event time is bounded by a positive value. This is required to avoid the Geno free behavior, because here the sampling is not time based, it is event based. So that's why it may happen that in a finite time interval you can finite time interval, the infinite number of execution may be there. So to avoid that, you have to ensure that the T mean will be always bounded by the positive value. That is the difference between the TK plus 1 minus TK. And here interestingly is that the interesting thing is that the theorem shows that the steady state error of event triggered PI control is solely depends on the event threshold E bar. Hence, by decreasing E bar, the error can be arbitrarily small, which however increases the possible information exchange. Means this design of E bar is very important. If you make it very small, then what will happen, that E bar, if you make very small, it means that you will be very close to the reference trajectory, and add in the presence of disturbance, you want to be in very close to the reference trajectory, means you have to execute the control task, or you have to update the control signal more frequently. But if you allow to be inside a more wider band, then what will happen, you may compromise with the performance, but at the same time you can save the number of or you can reduce the number of computation. Okay, that is very common phenomena in event triggered control system. And now we have simulated it, and now I'm not going to spend much time here, such that some discussion can be made. And the same with some values we have simulated it, that E bar is here, we have taken 0.2, and it can be simulated for different values of E bar to see the performance. And for 0.2 we have found that the performance is something like this. You see this Y, the red color curve is the YCT, that is the performance of the continuous time system. Okay, and Y of t, that is the blue color curve, is the performance of the event based system. And in case of event based system, you see we have defined this E bar basically, and whenever the trajectories will be inside this E bar, then only we are going to take the sample, otherwise not. Okay, so now you will find that the control signal is also like this for continuous time, and for the event based you can see the difference, that it is updated only when it is required to be updated, otherwise it is not, it is kept constant. You see here it is kept constant. Now, and you see these are the number of events actually it is generated, and it is very evident that you see at the beginning number of events are more. Why? That is exhibited in the control action also, if you follow the blue graph. So number of control execution is more, because at that time it was outside the band, and once it is inside the band, the occurrence of events are very less. And that is the advantage of event based sampling. You can say that we are almost achieving the similar performance, but at the cost of less number of control execution. And that is visible for the inter-event in the plot of the inter-event time also. This is the plot of tk plus 1 minus of tk, and you see initially it is very, and first of all it is positive, minimum value is positive, and as the steady state value or steady state performance is achieved by the system, then the system is relaxed. Very rarely we are executing the control task. Okay, otherwise initially the number of control execution of the control task were more, but as the system has reached to the control steady state value, the control task execution is lesser. Okay, and second example we have taken, I'm not going to spend much time here. The same thing, PID algorithm we have for tracking performance we have done, and for a DC motor. So that's why a DC motor, a second order model of the DC motor we have taken, and we have done the tracking performance of this reference signal, and we have compared their performance of time triggered, means periodic, as well as the event. Okay, this is the error between error of the trajectory tracking, you can, or tracking performance. Okay, almost here you will find that they are inside a band. Okay, but in case of time triggered we are getting perfect tracking, which is not possible in case of event triggered tracking. And most interesting thing is that we are not losing that, or we are not I want to say that we are compromising the performance of the system little bit, but we are gaining in other way, that we are saving the number of control computation, and that is reflected in this figure. You see this red line is the cumulative triggering in case of time trigger, which is almost like 3 into 10 to the power 4 means it is basically 30,000 number of control computation. But if you go for event triggered case, you see the number of computation is very less. It is almost 14,490. So at 50% reduction in the control update. So means you can save the energy, you can save the control computation, means computational facility you can save, and also you are not sending the control signal frequently through the channel. So channel will be free for the other applications. Also you can avoid the adverse effect of the networks. That is also very important. So I will end with the in general discussion that what actually the event triggered setup you have. So suppose if you have a x dot equal to ax plus bu, and you have a state feedback control law ut equal to k into xt, and if you are implementing in continuous domain, it is very easy to establish stability system arbitrarily. But same thing if we want to implement this state feedback control law using event based, then you know that there will be a generation of the error, that is xtk minus xt, because this error will be grown in the system because you are not taking the sample regularly. So now if you incorporate this error in the closed loop system, you will find that it is different from the earlier one. A term additionally is going to be introduced, that is bk into et. Now just you think, if I want to, it is the event based sampling if you do. Now if we want to stabilize this system, then only AB pair is controllable, it is not sufficient, or we cannot ensure that, means we cannot say that if the eigenvalues of A plus BK is having negative real part, it is stable. We cannot, no longer we can say that, because here a unknown term is there, BK into ET. And to stabilize this system, if we able to ensure the ET is bounded, and then we can ensure the stability, and the boundedness of ET will give you the triggering condition. So that is the main features you can say to evaluate what should be the triggering condition. And you see, for this system, if I want to evaluate the stability using Lyapunov function, then it is a linear system. So we have taken x transpose px, and then we are finding that minus a square norm of x square is there, but additionally this plus norm of et square is there. So to make it negative semi-definite, what we will do, we will take a condition that norm of et will be always less than equal to rho into a into xt. So now if you substitute in that condition, it is stable. So now this condition can be taken as a event triggered condition, means we are going to update the control signal only when it is going to violate this condition. So it is a state dependent, you can say that triggering condition. And with this, we can conclude that with the event triggered control, the reduction of computational effort and uses of communication channel can be achieved. The steady state bound can be designed as per any desired value, because that depends on you, that how close you want to achieve the system performance. And then you have to be balanced between the number of event, means number of control computation, and the performance. The optimum uses of resources can be achieved. And now there are, you will find that plenty papers nowadays and plenty works are going on in this direction, that observer based event triggered control, robust event triggered control. Maybe Abhishek has discussed about how the event triggered implementation can be done for a robust control, that is sliding mode control, and periodic event triggered control. You will find that here the event has to be monitored continuously, which is little bit of not feasible in case of discrete time setup. So it can happen that you can also observe the states to decide about or to evaluate the triggering condition periodically also. That is also a path of research. Then event triggered control for nonlinear system, that is also a very important research area, and the application of the theory of event based control. So theory is there, but what will be the performance for a practical system? That is very important. So in that regard, here some of the references are there, and in that regard, I'm showing you that we recently we have published a paper on the implementation, that is event triggered sliding mode control of two-wheeled mobile robot and experimental validation. So we have designed an event triggered sliding mode control for a two-wheeled mobile robot, and that design, you can, if you go through this paper, you can understand. And just to show you a result, that event triggered sliding mode control for a WMR, I'm showing this. You see, so this is the result we got, and this is working fine. So these are the few references I have mentioned. Those who wanted to start the research in this direction, they should start with all this basic paper. So I think I will stop here, and if anyone having any queries, then we can discuss that one. Okay. So this was the intention to discuss with you. Let me know that you have any queries. Ma'am?
Yeah. Participants, if you have any queries, you can ask.
Yeah, you can ask me anything if it is not possible to answer, or you can type in the chat box also, that I can see. So if you ask me, then only some discussion can be made. Okay, anyway, if you are not ready to ask now, so I have the email ID. Okay, I'm writing my email ID in the chat box. You can mail me regarding this also later on. As that we can, if you later on, if you require any help in this direction or any collaborative research also we can do. If you're interested, then we can start. Okay, so this is the thing. So Lalpriya madam, you will not ask anything to me? Lalpriya madam is here.
Hello, Manas. So that was a great talk and a great your paper. Everything is fine. Did you do all the experiments like in the DC motor and also the?
No.
This was
This
done in
is
your
a so this is a simulation only, but the mobile robot what I have shown, that is actually the result, practical result. But any UG student, if they wanted to do in the this DC motor, they can do. And recently, actually, that Indian Control Conference also, we have published one conference paper that we have implemented the PI controller, the event triggered PI controller on converter also. So that yeah,
So that is coming up in the 7th ICC.
Yes. This recent one. This recent ICC in IIT Bombay, there is I think 19th, from 19th it is
20.
so,
Yeah, it's starting from 20. Yeah.
20, yes, like that. So we have implemented it on converter also. So that result also you can see.
Great. Yeah. Okay. So that was a great talk, Manas. Yeah.
Thank you, ma'am.
All right. Thank you.
Okay, madam, if there is no queries, then you can conclude.
Okay, we'll conclude the session. Here I have Shilpa with me to deliver a formal thanks.
In this section, we are enlightened by a great presentation delivered by Dr. Manas Kumar sir. Sir, you have explained the event-based paradigm from its basic concepts and provided us with a good overview about Lyapunov's stability theory through examples. Thank you, sir, for sharing your valuable knowledge and time with us. So, on behalf of our Triply department, GC Trishur, and all the participants, I extend our sincere gratitude towards you, sir. Thank you once again. Our next section will be on Introduction to Nonlinear Dynamics, and it will be starting from 2 p.m. onwards.
Okay, so thank you once again that you
Thank
have
you,
given
Manoj.
opportunity. Yeah, thank you.
Yeah.
Yeah. So
Okay,
I'm
thank you
leaving.
so much.
Yeah.
Yeah, fine.
Yeah.